Nowadays, AI is everywhere, from generating images to your YouTube home feed to search engine results to large language models like ChatGPT. AI has become an essential part of our day-to-day lives. Now let's dive into curve fitting, the fundamental idea behind neural networks. Neural networks are functions. A function is like a machine that takes in a number or a series of numbers and spits out another series of numbers. The value of the output number depends only on the input number, and we can write an expression to represent how the output number is calculated. But first, let's look at the simplest function, a line. A line is written in the form of y equals mx plus b, or f of x equals mx plus b, where m is the slope and b is the bias. The slope and the bias can be any number, and they affect how the output is calculated. The slope is multiplied by x and determines how steep the line is, because for larger values of x, the slope influences the output value more. The bias is also called the y-intercept, because it's the value where x equals 0 at the y-axis. The slope and the bias define a line. Now suppose we have a set of example inputs and outputs that we want our function to satisfy, or at least close to satisfy. These are called data points, and we want to fit a straight line through these points. This is called a linear regression. The blue data points represent the desired function, some sort of real-world relationship that is influenced by random noise. Think of it as tweaking two knobs or parameters, the weight and the bias, so that the line can pass as closely through the data points as possible. Well, how can we calculate the discrepancy between our computer's model and the real thing? First, we take the difference between the data point's value and the predicted value by our model. However, some of these differences are positive and some are negative, and we can't just take the absolute value, since that's not how data in the real world works. So instead of just taking the linear value, we take the squared value. We then add up all these squared differences and then take the average. This is called the mean squared error, mean meaning average. If we graph the parameters a and b on a graph, each point corresponds to a single line. This is called a parameter space. Now let's say we only have one parameter a, and the loss or the mean squared error is only dependent on that one parameter. We can graph the loss as a separate axis, and then there's a curve. This is called the loss function. This loss function here is a parabola. We want to find the value of a that minimizes the loss, since minimizing the mean squared error means that our function fits the dataset very well. But how do we find this value of a? Well, we could loop through all possible values of a and find the one that leads to the least loss. But then if we have two parameters a and b, and then we have to find the a and b that gives the least loss, then we would have to loop through all possible pairs of values a and b. And then in cases with thousands of millions of parameters, this will be extremely inefficient. You first start at a random value or combination of values for the parameters. In this case, you're essentially a blind person trying to get down a mountain. You have limited access to the heights of the terrain around you, the values of the loss function, because that is extremely inefficient. And then you are trying to go downhill. If you were the blind person in this situation, you would probably feel the slope of the ground beneath your feet and then go in the downwards direction. This is like a ball rolling down a hill. It automatically goes to a relatively low part. This is gradient descent, how neural networks learn. But what is the slope beneath your feet? How can it be expressed in terms of numbers? For the people here who know calculus, you can skip this part. Remember the slope for lines, which is how steep the line is? We're going to do this for any point on any curve. You take 2 points that are close to each other, and then you take the ratio of the vertical difference to the horizontal difference. Remember that this difference is not absolute and can be negative. This is the slope of the line that connects these 2 points. If you take 2 points on that line with the difference of x being 1, then that slope is the difference of y. If the x-axis was time and the y-axis was distance, then this value, the rate of change, would be speed. Now we let these points get closer and closer together, with the distance between them approaching 0. This distance can't actually be 0, because then we would be dividing by 0. This number that gets infinitely close to 0 is called the Greek letter delta, which is a triangle. You can think of delta as a really small number. When the distance approaches 0, this line becomes the tangent line, or the line that only touches the function at one point. This slope of the tangent line, or the instantaneous speed at that point, is called the derivative. Here, if we graph the derivative of this function, we get this. When the original function is f of x, the derivative is denoted by f prime of x, which is f with a bar on top. You can also call it d over dx f of x. Here, if we graph a sine wave, we can think of it as a ball connected to a spring. The derivative is the ball's speed at any point in time. Here, the red function is considered the derivative function of the white function, and you can see that peaks in the red function correspond to parts in the white function where the graph is going steeply up, where the slope is very high. Meanwhile, the peaks and valleys of the white function are parts where the red function is 0, so you can see that the ball isn't moving at all. Now that we've learned about derivatives, let's get into neural networks again. This is a line f of x equals ax plus b. Now we subtract c, which is the test data point that we are trying to predict using ax plus b. Now we square this difference and we get the squared error, and if we average up all the squared errors, we get the mean squared error. But now let's look at just one data point and see how one parameter affects the squared error. We want to minimize the squared error by adjusting this parameter using the gradient or the derivative. We can take the partial derivative with respect to the parameter a. The partial derivative is when more parameters are involved, so the other parameters must also be inputs to the function. The partial derivative is represented by lowercase delta over lowercase delta a. To find the derivative, we can first split the function into two separate functions, f and g. Here x, or a in this case, is first passed through g, and then the output of that is passed through f. To find the derivative of the output with respect to x, we first find the derivative of g with respect to x, and then we find the derivative of f with respect to g's output in this situation, because the derivative of g is scaled by the derivative of x with respect to g. So it's basically the g function's derivative scaled by the f function's derivative. Notice that we have to know the g function's actual output and the actual input, because the f function's derivative takes the g function's output in as the input. Now let's first find the derivative of this part. Finding the derivative with respect to a, so we only care about things that contain a in this situation. B and c are constant, so they won't affect the output at all. Now ax is just a line. A is scaled by x, so the slope is just x. So the partial derivative of this expression with respect to a is just x. Now our second function takes the first function in as the input as x. The squared function is, well, just a square. Let's add a very small number, delta, to x to see how x squared changes. This is just geometry. We can see that there are two rectangles that both have the area x times delta, and then there's one small square that has the side length delta, so it's delta squared as the area. The new area added is obviously scaled by delta, so now we divide by delta. We get 2x plus delta. Remember that delta is a number infinitely close to 0, so when we add it, we can just remove it altogether. So the derivative of x squared is 2x. So using the rule we discussed earlier, the output of the first function, ax plus b minus c, is passed into the second function, x squared. Now we take the derivative of the second function and replace x with the first function. Then we multiply the derivative of the first function, x. So in the full form, the derivative of the linear squared error function is 2x times ax plus b minus c. Okay, back to the loss function. The derivative points in the upwards direction. In a simple line, the derivative is positive, so if you increase x, you increase y. If you want to go down, you decrease x by the derivative. This is gradient descent. You descend along the slope of the loss function. Now let's find the partial derivative with respect to b instead of a. Ax and c are constant, so changing b won't affect them at all, so we can just ignore them. The derivative of b is just 1, since that's the line y equals x. As with last time, the x in the second expression is just ax plus b minus c. So the partial derivative with respect to the bias b is just 2 times ax plus b minus c. Now these are the derivatives with respect to the parameters of the squared error function. But to train our model, we need to sum over all the data points in our dataset. The thing on the left is uppercase sigma. It just means summing over all cases of I, the data points. So it turns out the derivative of a sum is just the sum of the derivatives. We add them up because their effects stack. Now that we know the derivatives of the lost function, now we can apply gradient descent with a and b. This is gradient descent in action. Now the squared error function is a parabola since it's a linear function squared. Let's say we want to know the derivative of this point. We can zoom in until it becomes a straight line. This line is completely flat. The y value doesn't change at all. This means that the derivative is 0. Let's look at a more complex curve. The tangent line at this point is horizontal, so the derivative is 0. The areas around this point are both lower, so this is what's called a local maximum. But what we're really trying to find are local minimums, points in the hill where balls will get stuck. Gradient descent will ultimately converge into one of these local minimums. You can actually solve the linear regression equation by setting the derivative to be 0 and then solving using algebra. This is the result.